Hey guys, welcome back for the fourth and final video in this series on time to event analysis. I'm John and I'm going to take you through an example using two sample data. All of the previous videos have been preparing us for this moment, so I hope you're ready. Alright, first a little theory. Consider two independent samples with data that follow an exponential distribution and priors that follow a gamma distribution. See, I told you that we would need that information later on. I know all of this talk about two samples can get confusing, but remember that a two-sample model is often easier to think of as two separate one-sample models, that is, as long as the data and prior are independent. That makes getting the likelihood function pretty easy to obtain. It is just the likelihood of one sample times the likelihood of the other sample. So aren't you glad we already showed you how to get the likelihood function for the one-sample model? All that we need to do now is multiply the two models together to get the two-sample likelihood function. Next, we need to derive the joint posterior density. I know that I sound like a broken record by now, but it is pretty simple due to independence. Let's look at it. So do you notice anything from the form of the equation at the top? That's right, it looks like two gamma kernels. Because of this, it's easier to talk about the joint density in terms of the two single samples. So the posterior distribution of theta 1 given t1 follows a gamma distribution where the parameters a and b now consist of the sample size of sample 1 and the median of time 1. The distribution of theta 2 given t2 is similar, but with values that come from the second sample. It could be shown that 2 times b1 plus n1 times the median time 1 times theta 1 given time 1 follows a chi-squared distribution with degrees of freedom a1 plus n1. If we divide the two here, we get a ratio of one chi-squared distribution over another. This is its own distribution, which is known as the F distribution. Notice that the F distribution has degrees of freedom that come from the two separate chi-squared distributions. The ratio of theta 2 over theta 1 is commonly referred to as the risk ratio. It provides useful information for us, so we want to get a probability interval for it. Using the F distribution definition, if we isolate the ratio theta 2 over theta 1, we end up with this equation right here. We replace all of those nasty parameters that are constant with this C just to make it look nice and less scary. And this is the probability interval for theta 2 over theta 1. Okay guys, the data that we will be using is on the survival times in weeks of patients who were diagnosed with leukemia. The patients were classified according to two characteristics of white blood cells referred to as Ag positive and Ag negative. The 17 times from diagnosis to death for the Ag positive group and the 16 for the Ag negative group are given as N1 and N2 in the code. We define the times to death for each group as Y1 and Y2 respectively. Also, I want to point out that the package that we primarily use for time to event analysis or survival analysis is the survival package. Go figure. So let's run the code I mentioned before. Okay, a useful plot that is pretty easy to create is a histogram plot. Here's the R code for that plot. We plot the two histograms of the groups in one picture so that we can directly compare the two. We could see that the histograms in the plot here show that empirically at least, the patients in the Ag positive group tend to have better survival prospects than the Ag negative patients. Note that there is no censoring here, so every patient observed did have an event. Another plot that we will be looking at is of the prior and posterior of theta 1 and theta 2. This is useful in showing how much the distribution has changed once we have gathered data and often tell us how reliable our prior information was. If the posterior distribution hasn't changed much, that means that the data agrees with our prior knowledge. Here, we have the leukemia data as well as values of our choice of priors A and B for both samples. The choice of prior A and B is done using the find gamma function here. And here are the numbers to be saved. And here are the posterior and prior for gamma. All right, now let's plot the graphs. So we can also compare, or as you can see, the guess for theta 2 was a little bit more accurate compared to theta 1. We can also compare the Ag positive group with the Ag negative group and notice that the Ag positive group's distribution is more narrow compared to the Ag negative group. I also plotted the HPD intervals for each group so that we can see that as well. And you should try to gain as much information about the thetas as you can from the graphs, as it is the easiest way to understand. I mean, if I showed a 10-year-old kid these plots and asked them which value is bigger, they could probably figure it out. But if you completely hate the visual route, I also have the summary for the two groups here. But I want you to know that you are a very boring person. Next, let's look at the risk ratio. The risk ratio is important in the fact that it puts risks into context. If I told you I got an 85 on an exam after staying up all night to study, you might be impressed. But if I told you that someone else spent the same amount of time studying but slept 8 hours and got a 95, then you might have an idea of how important sleep is for an exam. That is what we are looking at here, the ratio of Ag negative over Ag positive. That will tell us how important being Ag negative is for leukemia compared to being Ag positive. So here's a code for the posterior density of the risk ratio. You can also see the HPD interval in the plot. Taking a closer look, the mean risk of death from leukemia for Ag negative patients seems to be about 3.5 times higher than that of patients with Ag positive characteristics. The 95% HPD interval is from about 1.5 to 6. We can then safely conclude that patients with characteristics of white blood cells, which we refer to as Ag negative, do have a higher risk of death due to leukemia than those classified as Ag positive. For an exact 95% probability interval for the risk ratio, refer to this code here. We can see that it goes from about 1.7 to 6.4. So this example doesn't really have much to do with time to event analysis, as it doesn't have any censored observations. So now let's look at the same problem but add in a fake random censoring to see the changes that occur. Imagine that the study conducted only lasted a year. So all the times of death that were above 52 previously are now going to be considered censored observations. The line that has delta 1 and delta 2, they are the censored indicator for groups 1 and 2. Remember, a delta equal to 1 means that the observation had an event, while delta equal to 0 means a censored observation. We also have to add a subset of observations that include only those that were uncensored. And we do that here. So let's run this whole chunk of code. And if you are observant here, you'll know that you can note that everything else remains the same except you replace the N1s with the new NU1. and the old y1 is now replaced by the censored y1 and y2. So knowing that, I'm not going to go over all of the R code again, but I am going to show you guys the plots and the values of interest so that we can see how they compare to the previous example. Let me run this. So here is the prior and posterior plots. The plots look very similar to the non-censoring case, and this is primarily because most of the censoring came from a single group, and that's the Ag positive group. This means that the time of death for Ag negative is still going to be below that of Ag positive. Unless we make the censoring take place in like 1 month, our results will largely be the same. And then here is the risk ratio. First, I'm going to show you the summary in case, again, you're interested in hard numbers. And now let's look at the plot. And it's the same for the risk ratio. The numbers are still pretty much the same. The key thing I wanted you guys to learn is just how to set it, how the setup is different. This way, you will know what to do when the data is truly censored. Anyway, that's it for this one, guys. I had a good time teaching you some of these Bayesian concepts, and I encourage you to learn more if you can. I believe that Bayesian statistics is something that every aspiring statistician should be familiar with. Anyway, that's enough rambling from me. Again, I'm John, and I wish you guys good luck in the future.